All right, how's everything going today? So I want to talk about ODP 209, which was posted this morning, and then I want to talk about hashes. So any questions before we go into that? The left front room disappeared. So 209, we're working with a linked list still. One switch up, we don't have a sentinel node in this list. Okay, so the first node of the list is actually the first data node. So no sentinel. You're creating a function called edit. And edit takes a pointer to the first node, and it doesn't return anything. So it's returning a type void. And your edit function should delete that middle node. So just remove that node in the middle of the list. And I'm guaranteeing to you that when I call edit, I'm going to pass it a struct node pointer. It's not going to be null. Okay, it's going to point to a node whose next field points to a second node, whose next field points to a third, whose next field is null. So that's what the argument will look like. It'll be a pointer to that first node. And you should write code to get rid of that middle node.
Should we free it?
Don't print anything.
No, free it.
Oh, free it. Yes, go ahead and free it. All right, so we know where the first node is. That's the argument we're passed. How do we know where the second node is? Yeah, pointer, arrow, next. And if we put that in a variable, we've got a pointer to that middle node now. We can get to the third node the same way. That's just that variable, arrow, next. Or it's pointer, arrow, next, if you like. So your whole task is to take pointer, arrow, next and set it equal to the address of that third node, and then free the middle node. So a few lines of C, depending on how you code it. Do you use temporary variables and so on? Code that up and assess it, and you should be good to go. So the previous section, I told them I was going to post 210 tomorrow morning, and they asked if I could post the README ahead of time. So the README for 210 is already on the temp area, but don't assess it until after 8:05 tomorrow morning. So, and we'll talk about it tomorrow, but if you want to get a heads up, it's in there, but with a little disclaimer on the front. This ODP doesn't open until Friday morning at 8:05. So don't read this and get all excited and go ahead and do it and assess it, because you'll clobber your grade on 209. So, but if you wanted to get a heads up, and this is just going to insert a node into a list, which is another thing you're going to do in PA too. So, but we'll talk about that in detail tomorrow. All right, so any questions on 209? Yeah.
So we don't have to create new stuff, right?
No, for 209, you've already got all the nodes there. You're just moving one to the other. That's not 209. That's tomorrow's. All right, good. So, so we've also got this student satisfaction survey we're going to do the last 15 minutes of class, unless I forget and just keep talking the whole time. But your section has been chosen to complete a student survey, and they say it'll take 10 minutes, but I'll try to stop like 15 minutes early and give you a chance to do that. Also, I got an email this morning. There's going to be an unannounced lockdown drill sometime, somewhere. I don't know when or where, but if alarms go off at some point during class, that's probably what it is. So let's talk about hashes. So basic idea of a hash. So what are we doing in data structures? We're storing information in a computer, right? That's the essential thing we've been talking about. Mostly we've been storing collections of numbers. We can store them in arrays, we can store them in a list, and in the list we can do easier insertion in the middle of the list and so on. But why would we want to store a bunch of numbers in an array or a list or some kind of structure? It doesn't really do us a whole lot of good, right? Those numbers might be student IDs, but there'd be no reason to just have a linked list with a gazillion student IDs in them. It doesn't do us anything, right? We could store grades and have 100 grades in this array, but what does that mean? It's just numbers. So usually when we're storing information in a computer, we have multiple pieces of information that we want to have associated with one another. So for example, we might have a name, and we might have, let's say, an extension. So the extensions, those are going to be 4-digit numbers. And we know we can store those in a linked list and so on. But seeing 2115 doesn't do us any good. We got to know that that's associated with Nick. So how can we store these extensions in a way that let us get to them from a person's name? We can use our parallel array structure. So I'm going to store the name Izad, and I'm going to store his extension, which I don't know, so he's going to be 1234. And we can store Tina, and I don't know her extension, so she'll be 9867. And I know my extension, so I can put 2115. And we'll go ahead and put in Carol.
Oh, that's good.
Do you know her extension?
Yeah, 2245.
Oh, nice. Okay. Got data exposure in 222. All right. So, so now we have some information that's associated with each other, and this is useful. So these are parallel arrays. So there's indexes associated with these. So you come to this collection of data and you say, hey, I want to know Nick's extension. So what do? You search the name array for Nick. Not Nick, not Nick. Hey, there's Nick. Where is Nick stored? Index 2. Go to the extension array, index 2. There's Nick's extension. Okay, nothing magic going on here. Now, if I want to search for Keith's extension, not Keith, not Keith, not Keith, not Keith, we're out of possibilities. Keith is not stored in here. His extension's not found in this data set. Okay, the problems with this are efficiency. Searching for a name takes us order n. So remember, order n says if you have n pieces of data, it takes you roughly n operations. Meaning if you have 100 times as much data, it will take you 100 times as long to do the same operation. So the growth is linear. And that's not really ideal. Right? If you imagine Google, if they were trying to store pages and they started off with 1,000 pages and now they've got 100 billion pages, right? Their problem size has grown by 100 million. If it took, half a second to do 1,000 pages, now it would take 50 million seconds to do 100 billion pages, right? So linear is not really great. So order n is our search time on this array. And as this grows, that's not really ideal. Now, if we alphabetize this, we know we can do a binary search. But remember, the problem with alphabetizing is then this has to be ordered, so if we want to insert something in the middle, we have to move everything down. So we could make this a list and make that a list. But to move through the list is order n, right? To search for a name is back to order n. If we want to insert something, that's very efficient, And if we want to delete something, that's sufficient. So we're dealing with order n, and even if we move these things into what we're going to study later, which is trees, we can get this down to something like log n. But that can still be pretty significant. And really our ideal performance is order 1. And order 1, so this is ideal. To say something is order 1 means it always takes one time unit. 1 second, 1 day, 1 microsecond, 1 something, right? 1 chunk of time, 2.75 milliseconds. But it doesn't involve n. So an order 1 algorithm would take the same amount of time if you had 10 pieces of data or if you had 10 billion pieces of data. The time doesn't get any worse. That's a really nice place to be, because now you can grow your problem set and your algorithm runs just as fast. And that's hard to imagine how that could happen. But our brains do this to some degree, at least it seems like it. For example, if you look at a picture of faces in a crowd and you're trying to pick out one particular face, we can do it pretty quickly. We're not usually looking at each face, going across and then come down and look at each face. Somehow we can look at the whole picture, and if we're looking for the one person with blue hair, it's pretty easy to pick them out. And if you have 10 people or if you have 1,000 people, it doesn't seem to take 100 times longer with 1,000 people. So things like this pop up around us. Can we do this in a computer? And the answer is yes. We can get pretty close to order 1 for storing and retrieving this kind of information. This is what a hash is going to do for us. Okay, so how do we do this? Well, the problem is if I want to know what Tina's extension is, I have to look through here and figure out where Tina is stored. I have to figure out what index her information is at. Once I find her in here, index 1, it's immediate to go over here and just read the extension stored at index 1. That part is fast. Doesn't matter if there's 3 things in here or 10 million things. If I know the extension is at index 1, I can just go right there and read it out of memory. The trick is, how do we know that that information is at index 1? Well, right now we know it because we searched here and we found Tina was at index 1. So let's change that up. So here's what we're going to do. Same thing. I'm going to make these arrays a little bigger. I'm going to make them 27 entries. So they're going to go from 0 down to 26. Okay, so we're going to load information into these arrays. So the first thing we get is Izad, extension 1, 2, 3, 4. Instead of storing it in the first open location, here's what I'm going to do. I'm going to look at the first letter of this name, I. And I is the 9th letter of the alphabet. So I'm going to store Izad down here at index 9. And now I want to store Tina. And I'm going to look at that first letter, and that's a T, and T is the 20th letter of the alphabet. So down here at location 20, I'll store Tina, and at index 20 in the extension array, I'll store her extension. And this is how I'm going to store my information. So Nick, 2115, N is the 14th letter. So there's Nick, and there's the extension. And Carol is the 3rd letter. I'm going to have memorized our extension by the time we're done here. This is good. And so there's how we'd store this information. Okay, what have we done? We've made our search really, really efficient. So come to your data structure. I want to find Nick's extension. Look at the first letter. Subtract 64 from its ASCII code, because A is code 65. Subtract 64 from the ASCII code for N, I get 14. Go to entry 14, there's my extension. Magic. Okay, so the way I've drawn this out, this is order 1. Because it doesn't matter if Carol's the only entry in here or if there's all these other entries. I don't have to deal with these. Carol, C, index 3, 2245. Okay, basic setup for a hash. Lots of details, lots of complications. But that's the basic idea. We have some sort of thing that we're using to retrieve our information. So this is more generally called a key. And the piece of information associated with the key, we can just call that a datum or a data. Yeah?
What about if I have 100 different names? Can I still use this way to store the data?
If you have what?
100 different names, like not
100 names is going to be a problem.
Yeah.
Because this table is only big enough for 26
26.
names.
So 27 names is going to be a problem.
Yeah, guaranteed.
Or what if we have like
When you start
for
with the
Nick
next
and
letter.
then Nigel and then Nate, so like people with the same like first letter and then.
Right, so if you have two people with the same first letter, they're going to go to the same location. So what was your comment?
Then you just look at the next letter
Could look at the next letter.
from that subset.
Mm-hmm. Cool. Okay, so this is the biggest issue with hashes, is that unless your array is big enough to hold every possible name, you're going to have multiple names that come into the same location. Okay, it's guaranteed. This is something called the Pigeonhole Principle. If you're in 215, we're going to learn that in a few weeks. Now, if we have 10 character names, 26 letters, that's 26 to the 10th possible names. If I made my array that big, I could have a separate spot for each possible name. That's usually not feasible. So usually we don't have enough space for every possible name, which means there's a possibility of what we call collisions. So collision is when two things try to go into the same location. So let's say we want to store Craig, and their extension is 0001. While we look at the first letter, it's a C, that should go in location 3. We come to location 3 and we say, oh, somebody's already here. So that's a collision. So it tries to store Craig at 3, but that location is occupied. So hash collisions are the fundamental problem. There's a few things we can do here. So ideas.
You could put it in the next slot.
We could put it in the next slot. We could say, okay, well, can't put it in 3. Let's just go down to 4. 4 is open, so we'll store Craig there. And we'll store their extension. So that's something called probing. So if there's a collision, find a different spot. try to find a spot that's available and store the name there. That's going to be our preferred way of doing this, but it complicates things because now if we want to find Craig, we would say, okay, Craig is a C, they should be right here, we're going to find Carol instead. So we're going to have to deal with that. But that's going to be the approach that we take. But a different approach might be to make a two-dimensional array so that we could have multiple entries at location 3. We could have Carol at 2245, we could have Craig at 001, and so on. And we could have parallel arrays at each of these locations. But we don't know how big those arrays should be. We'd like them to be able to shrink and grow accordingly, so what's better than an array if we want it to be more dynamic?
A vector? A structure? A linked list?
A linked list, which is also a structure and kind of like a vector. Yeah, we could put a linked list at each of these. So at location 3, we would have, say, a sentinel node, which points to a linked list whose first entry is Carol 2245, whose next entry is Craig 0001, and so on. So we don't have to look for different locations in here, but now our performance starts to degrade.
Recursion, you can make it just look at the next letter and do that alphabetical thing.
Yeah, so we could do different versions of probing, right? We could go into the second letter and use that to give us a location to look for.
Until you have 26 different versions of that combination.
Until you have 26 different versions of that.
Recursion again.
And then you can recurse again. But if once your table's full, then you're out of luck.
Until you have two people with the same name.
Yeah. So chaining,
That's the case, then you're just out of luck.
then you're totally out of luck. Just put them in the same phone extension. So chaining, so each entry in here could actually be a linked list. And everybody whose first name starts with a C gets put in this linked list that's stored at location 3. Right? Performance takes a hit because linked lists aren't efficient. If you had 1 million people with the letter C, you get here really quickly, order 1, but now you have to do 1 million operations to search through that linked list. So chaining's not bad if you're only expecting a few collisions. If your maximum length of a linked list in this case would be 5, right? It's order 5, which is order 1. But if it could grow indefinitely, that's not optimal. So we usually do probing, which is if there's a collision, we're going to find a different spot. Okay, so a simple version of probing is just look in the next location. So Craig should go in 3, that was occupied, put it in 4. Okay, so Ellen comes in. 1, 2, 2, 1. Ellen is an E, is a 5. Goes right here. This is free. There's Ellen. There's 1, 2, 2, 1.
First thing you have a problem if you get David.
You got a problem if you get David or Cat. So yeah, let's do David. So David D, that's a 4, comes down here. 4 is occupied. Let's put David in the next spot. Well, the next spot is occupied. That's Ellen. Let's try the next spot. 6 is free, so we put David right there. Okay, this is starting to look like a mess because our name array is not even alphabetized anymore. But we can still work with this. So if you want to find David's extension, take their name, D, go to location 4. That's not David. Check the next location. That's not David. Check the next location. There's David. Okay, now suppose you want to know what is Doug's extension. Same thing. Doug is a 4. That's not Doug, go to the next. That's not Doug, go to the next. That's not Doug, go to the next. That's empty. We're done. Doug's not in the table. Got the idea? Yes?
Good. I feel like there still could be be a chance for order n? Let's say that all the...
Oh yeah, definitely. Yeah, once you have collisions, your order starts to degrade. And the more collisions, the worse it gets. And if you have a collision where there's a block of, you know, 1 million names that all hash to the same location, yeah, it could take you 1 million operations. So this kills your performance, and that's why we don't get the ideal order 1 in all cases. But if we're really good with how we write our function to tell us where these things are stored, we can avoid collisions to a large degree. Okay, so hash function. So this takes a key, such as our name, and it returns an index. So our hash function so far is fairly primitive. Just take the first letter, whatever letter that is in the alphabet, that's our index. And we can tell it's not good because lots of people have first names that start with the same letter. Right? Some letters are... Every class I teach, there's always like one dominant letter. And I think K is it right now for 222 across the sections. I've got so many people whose last name starts with K. I don't know why, but it's different every quarter. So, and first names are probably the same. So this is not an efficient strategy. Let me show you a possibly better. So example. So this is a hash function h. Takes in the name. Take name, element 0, subtract 64. That's the one we've been working with. So cat goes to 3, Abe goes to 1, and so on. A better one might be this. Make a loop from 0 to the length of the name minus 1. Add up the ASCII codes of each character in the name. Take that whole thing and reduce it modulo 101. So make these arrays 101 elements long, going from 0 to 100. And for each name, add up their ASCII codes, divide by 101, take the remainder. Use that as the index. That's going to have the advantage because Nick Jones and Nick Smith will hash to different locations probably. Right? It's not based just on first name or beginning letter or last letter. Are you still going to have collisions? Absolutely, because we've only got 101 possible locations that we can map to. And if you take more than 101 names, at least 2 of them are going to map to the same thing. But the hope is that this is taking names and it's spreading them out throughout this array. So if we have 10 people whose first name starts with a C, this naive function would map them all to this location. And you get this big cluster. This function, depending on what the rest of their name is, will probably spread them out. So clustering is the effect when many names map near each other. And that's what's happening over here. We got a big cluster of names here. All of this space is like really sparse. From Izad down to the end, we only got 3 names, but we got a big cluster of them up here. So a good hash function will minimize clustering. How do you know what a good hash function is? It depends on your data. If you know that you're hashing names, or you know that you're hashing student IDs, you're going to use different hash functions. Here's a terrible hash function for student IDs. Let's just take the first 3 digits, and we'll get a number from 0 to 999. Terrible function because most students, their first 3 digits are 940 or 944. Right? Take the last 3 digits, that's a better hash function, because those, I think, are more uniformly distributed. So choice of hash function, that's a whole science in itself. All right, there's also a complication when it comes to retrieving data. So let's say we're looking for David. Let's say we're looking for Doug. We'll go back to Doug. So D is a 4, maps here, there's Craig, there's Ellen, there's David. This spot is empty. So we know Doug's not in there. Well, what do I mean by this spot is empty? Is there ever such a thing in an array in our computers? Is there ever a memory location that's actually empty? Right? There's always something stored in memory. It might have garbage in there, but unless we have a way of knowing this is not a name, this is just garbage, we don't know if this is empty or if this is storing the name of someone whose name has a bunch of weird characters in it. So we need to augment this name with at least one more field, which we can call valid. And when we store a name in here, we'll set the valid field to be a 1, and it'll be 0 everywhere else. So now what happens when we look for Doug? Comes to a 4, that's not Doug, but it is someone, because valid is 1. Check the next location. That's not Doug, but it is someone. Check the next location, not Doug, but it is someone. Check the next location, not Doug, but that's not actually an entry in our hash. If Doug was stored here, we would have found them by now, so we can say Doug's not in here. This gets more complicated when you start deleting things. Because if I delete Ellen, this is going to go back to a 0. And I may not find David now. Because if I look for David, I'll start here, no. I'll come down to the next location, that's not David. If this valid flag is 0, I'm going to say David's not in here, when in fact they are. So we'll deal with that another day. But again, this is kind of a 10,000 foot view of hashing and hash tables. All right, I want to pass out this survey and have you do that. But we'll continue talking about hashing tomorrow, and we'll talk about hashes as associative arrays. So think back to when we talked about associative arrays. Go ahead and pass those around, please. Close your eyes, because I'm going to turn on the lights all at once. All right, and there's survey. So while those are going around, I'm supposed to read the back of this. So I'm going to stop recording so the world doesn't have to hear this.